Today I'm Ekin and I'm here to present our baseline submission for this HPA task. Laura already made an introduction to the task, and I'm not going to talk too much about why we are doing this task, but I just want to reiterate that the main cue that we want to use is it has been already shown in social sciences that speakers tend to act differently when they're speaking. And we want to use this cue for competitive performance. And we want to exploit two different modalities, and one is the wearable acceleration and the other one is video. So basically we want to detect these different movement patterns of speakers from acceleration and from video. And finally, we want to use some type of multimodal methodology that will help us obtain better results. So our proposed solutions for acceleration is transductive parameter transfer, and for video it's bags of dense trajectories and multiple instance learning via embedded instance selection. Don't worry, I will first explain why we chose these methods, and then I will explain what these methods actually are. Okay, Laura also talked about this, but apart from that, instead of only looking at the literature and saying that, yeah, the participants tend to move differently, we actually did some experiments in their data. We used the variance of acceleration magnitude and tried to see if these cue for movement is different for people while they're speaking and while they're listening or not speaking. And we find out that, yes, this is definitely different, but this difference is really varied per participant. So for some participants, it was really easy to distinguish between those two things, but for some participants, it was definitely unbelievably hard to do. So the difference per participant is highly varied, and for using this knowledge, we employ the transfer learning approach, where we treat each participant's data as a source set. So compared to yesterday's transfer learning approaches, we use something a bit more old-fashioned. So there are no neural networks and no fine-tuning of the layers. What we did is called transductive parameter transfer, and what we basically assume is for each participant I, we assume that there is this probability distribution Px, marginal probability distribution Px, that generates their data. And we want to learn a mapping from this distribution to the optimal parameters of a classifier for that data. So how we do this is we treat each participant. So when we are trying to classify data for a new participant, we treat other participants' data as source sets, and for each source set, for these source sets, of course, we have label information. We train we find the optimal parameters for an optimal classifier, and we do this by logistic regression. Then we create a training set which includes these parameters, basically the regression parameters and the intercept, and the distribution of this data. Then what we do is we try to learn this mapping from distribution to these optimal parameters. And in order to do so, we use a kernel, which is Earth's mover distance kernel, which can define distances between distributions. And we use this kernel to learn a mapping between the distribution and the parameters. And after we obtain this mapping, what we can do, we can just plug in the data of a test participant, and it will give us these optimal parameters for their classifier. So this basically kind of shows the image. So there's this data coming from one participant, other participant, then you're trying to find the parameters for a new participant. You learn this kernel matrix, which basically shows the similarities or the distances, as you want to say, between these source sets, and then you learn this mapping and obtain the classifier for the new one. I'm not going to go into details of the features that we use, but we actually use pretty basic features that that are shown in the literature to be representative of movement and action. So statistical features, mean and variance, spectral features, power spectral density, and we extracted all of these in 3-second windows with 1.5 seconds overlap from each axis of the acceleration, absolute values, and the magnitude. And after we obtained an estimation for these 3-second windows, we upsampled it, like basically like repetition and with some mean, to 1 second, because the task was to estimate in 1 second, but just using 1 second windows was not really informative. It was somehow hard to distinguish between different things. For the video, why did we use dense trajectories and miles? Okay, dense trajectories is known to perform really good in activity recognition. So this was something that we chose to use. But the more important part is like why we use multiple instance learning. Laura already showed how our data set looks, and it is really possible that you might have some trajectories in the video that is actually not for the person. It can be shadow, it can be some other person. So basically, like we have some trajectories, some of are good, some of are representative of the participant, and some are not. And for this reason, we propose to use multiple instance learning, where you have, okay, I'm just going quick. Where you have these bags, and the bags includes good trajectories and bad trajectories. And basically, what we do is we extract the dense trajectories, we cluster them spatio-temporally into these bags, and the miles, these multiple instance learning method learns to classify the bags. So you can have bad instances in the bag, but if there is good instances, then you will classify this bag as speech in our sense. And the multimodal fusion is just, we didn't do anything special. We get the estimations from acceleration, we get the estimations from the video, and in the end we average the estimations to get the final one. So these are the AUC scores that we obtained. You can see we have something close to 66% for acceleration and fusion, but we failed miserably on the video. But if we go and check per participant, we actually see that there are some cases where video actually performed much better than the acceleration. And the fusion, we cannot say that it's significantly increased, but it's still kind of better than the acceleration. And I think the scores actually show like how different these tasks, how challenging this task for different participants. So for some it is really easy to get it from acceleration, for some it is really hard. And so what we learned from this, we can still say that we have promising results. Okay, it's not perfect, but we are better than a random baseline, and we want to continue working in this direction. When we go and check why the video is not performing optimally, we have seen that there are many cases where the participants were actually out of the view. So we also, since this was a real life event, they just went to restroom, they went some other places, but so there are nothing, at this points, there's nothing to do for video because we cannot estimate anything. And we believe that with better video estimation and with a method that can actually exploit the multi-modal nature of this problem, it will be possible to acquire some competitive performance in the end. Thank you.